Welcome to Mathlink Academy, where we connect the dots. I am Mr. C, and in this unit, we're going to talk about optimization. In other words, we're going to look at how to apply the maximum and minimum problems. So that means we're going to be using the first derivative that helps us find max and min. So let's get started. So there's some, I'll say, rules or maybe some procedures you can use to apply for max and min problems or optimization problems. So the first thing you want to do basically is draw the picture of what they're trying to optimize. If it's a rectangle, box, whatever the case may be, let's first draw the picture. And with that picture or sketch the graph of it, we also should be given or see a primary equation. And then also we should have a secondary equation from what we see here. So a lot of times they say find the volume, then we have to use a volume, and then we may have to use something else. And then we want to combine those two equations to make it one. And then you want to basically take the first derivative, set it equal to 0, and get your feasible domain. You may end up with positive and negative numbers, but you may realize that I cannot use negative numbers because it doesn't make sense. So I may just focus on the positive. And then from there, answer the question when you solve for your unknowns, when you set your first derivative equal to 0. So let's kind of look at a problem and see how we can apply these different rules or even procedures of applying minimum or maximum problems in optimization. So we're going to look at a problem for optimization, finding maximum volume. And this is our problem that we're looking at. It says a manufacturer wants to design an open box having a square base, so the base is square, and a surface area of 108 square inches. And it's shown in our diagram here. What dimension will produce a box with maximum volume? So there's a few things that's standing out to me. Maximum volume. So let's jump in here. And I gave you the first equation a little earlier, and then I went back to the drawing. The first thing you want to do is draw the picture. So this is a great picture I've drawn. How many like that picture? Perfect, great picture. Square base, so it's an X by X base. So the base is square. And then we also have an open top. So there's nothing up here. So there's no surface area to worry about on the top. Also, it tells us that we have a surface area of 108. And we want to find a maximum value. So the first thing is draw the picture. Second thing is find your primary and your secondary equations. So one of my equations is surface area. And so what I look down here, I'm circling the base, and the area of just the base that I circle will be x times x. It's a square. So x times x is x squared. So I'm going to just write that down. That's just the base. Now I need to find the sides. Now the sides are going to be a little different because they're not going to be x times x. This is one side. This would be x times h. Here's another side. It'll be x times the height, x, h. And the other side be x times h, x times h. So we have 4 different sizes with x times h. And when we add that, that'll be plus 4x times h. And that's going to equal to 108. So that's my surface area. I don't have a top to worry about, just the base and the sides. So let's rewrite that again. So we have the base being x squared plus 4 times x times h, which is 108. The other piece is the maximum volume. How do you find the volume of this particular shape? I'll use V. V is equal to, how do you find the volume of this box? It'll be x times h. Or another way of saying it, it'll be x squared times h. So here's our 2 equations, our volume and our surface area. Since we are running out of room on this slide, we're going to go to our whiteboard and do the rest of the work. So on our whiteboard, here's our two equations. One is surface area. This is our first one, and then here's our second one. Now, what we want to do, we want to maximize, I want to write this down. We want to maximize the value. So in other words, to maximize the value, we have to take the derivative of the value. It's like finding those critical values that we did in other videos that I've talked about. But for that to happen, notice the volume is equal to x squared times h. I want everything in the same variables. So what I'm going to do, I'm actually going to rewrite the top equation in terms of h. So h, we'll solve for h, that'd be 108. We're going to subtract x squared and then divide it by 4x. And that gives me h. I found h by itself using some algebra. I'm going to plug this value for h into this volume equation. And so that's how you optimize. What you do, you find two equations, rewrite one of them, plug into the other one so that other one only has one variable, x, y, z, whatever the case may be. In our case, we want to have all x's. So let me write this in black. So v is going to equal to x squared times our h is 108 minus x squared divided by 4x, and then simplify to make it easier for ourselves. And so this will cancel out with that x, and we're left here with 108 times x minus x cubed divided by 4. And another way we can say, and you may want to say where I get that 108x minus x cubed, what I did was I multiply the x all the way across the denominator. Don't forget there is an x right here, multiply it, called the distributive property, and write it that way. So another way I could write this is 1/4 times 108x minus x cubed. That's another way of writing it, and I'm going to use that as a way of solving for my problem. So my value is equal to 1/4 of 108x minus x cubed, if I'm not mistaken. Now again, the problem is asking find the maximum value. So we want to find the maximum value. How do we find the maximum value? We have to take the first derivative of the value with respect to x, because everything's in terms of x right now. And then what you do, you set that equal to 0, and that gives you your value for the x. So we're going to take the first derivative with respect to x. Now, since 1/4 is a constant, I could just leave that alone. I'm just going to take the derivative of what's inside the bracket. So the derivative of that will be 108 minus 3 times x squared. That's my derivative. Now, what I'm going to do with that, set equal to 0, because we're maximizing the volume. That's why we're taking the derivative and set equal to 0 and solve for x. The 1/4 will cancel. We won't care about that for right now. When we solve, we have, I'm going to write this in blue. We have 108 minus 3x squared equals 0. We have negative 3x squared is equal to a negative 108. X squared, get it by itself, is equal to a positive, I think, 36. And then we solve for x. Do the square root plus or minus square root on both sides. We end up with plus or minus 6 as an answer. Now again, remember x has to do with the length of the box, the base of the box. And so since it has to do with length, we cannot use the negative value. We only can use the positive value. So in this case, x is equal to 6. That's our answer. X is equal to 6. That's our length, 6 units, whatever units we're talking about. Now, we're not done because the box had a height and length, excuse me. So to find our h, we're going to go back to our original equation up here. Look up here, guys, that I saw for x. And then h will equal to 108 minus 6 squared, which is 36, divided by 4 times 6. 4 times 6 is 24. We'll do our math. I think this will equal to 3. So we was able to find h equals 3. So let me go here. So I'm going to go x here. So x is equal to 6. There we go. And h is equal to 3. Now remember the shape of the box and how to look. We had a box like this. It was open on the top. And we had x here, x on the base. And then we had the height, h, which is right here. So we want to find the maximum dimensions. So what will be the dimensions? So let's answer this question. What would be the maximum dimensions? It would be 6, the length, times the width. Those are the two x, times the height, which is 3. And so that will be our max, that'll be our dimension right there. And if we want to find the maximum volume, we just multiply those values. So it's really be 18 times 6 in our case. And then the maximum volume, I would say max volume. Again, be 108 cube, whatever our volume is cubic. So that will be our maximum volume that we have here, if I'm not mistaken. And this is the dimension to give us that maximum volume. For these optimization problems, remember, draw the picture first, sketch a graph. From there, we should be able to get at least 2 equations, a primary one and a secondary one. And then what you want to do is rewrite one of them and plug it into the other one, and then take the derivative of that second equation with respect to x or whatever variable you're working with. Set equals 0, that gives you a critical value, and figure out which critical values you need to get the remaining part of the answers. Hopefully this helped. If you have any questions, look back over the video and look at some of our supplementary material on our Mathlink website. Again, let Mathlink bring it together.